So we'll talk through the four different factors which Le Chatelier's principle states causes the position of the equilibrium to shift, and then we'll talk about the effect of Kc on each of those factors. Whether or not the value of Kc changes depends on the concentration of the reactants and the concentration of products. Okay, so if one of the four factors for Le Chatelier's principle changes the concentration of the products directly, that means the system tries to change itself such that the value of Kc remains the same. Okay, I'll repeat that. So if the concentration of the particles or the number of particles is changed as a result of one of those four factors, the system tries to keep the Kc value the same. All right, let's go through the different scenarios. So let's say you have this setup here, and we're talking about a change in concentration. So you've got A plus 2B gives you C plus D. It's a reversible reaction, and here's the expression for Kc. And what you would have here is, so let's say, another thing as well, by the way, I'll be using the ICE model, so and I'll be color coding them as well. So the initial setup is black, change is red, and the equilibrium setup is will be drawn in blue. Okay, so you've got the system here. It's black, so this is what we're starting off with. So this system is currently in equilibrium, and let's say, for example, we make a change to the concentration of A. So let's say we increase the concentration of A. If we were to increase the concentration of A, that will lead to this value increasing. Okay. And then the overall effect on Kc is it will decrease. Okay, denominator increases, the overall value of Kc decreases. So that's the change. So at the start I said, if the number of particles changes, the system tries to keep the Kc value to the same value that it was. So it tries to revert to the old value. Okay, hopefully you can see concentration of A increases, the Kc value drops. So what does the system do? It causes this higher concentration of A to react. Okay, it pushes the forward reaction or increases the rate of the forward reaction. Therefore, using up A, and if it uses up A, it therefore increases the concentration of C and D. More C and D are produced. Therefore, if the denominator goes down and the numerator goes up, the overall value of Kc will increase. Okay, so then, therefore, the overall Kc value increases at the new equilibrium. Okay, so hopefully you can see that if there's a change in concentration, the system works itself in such a way to return to the old Kc value. Right, now going on to pressure. So this should be Kp. So we've got the same setup over here, but now everything's a gas. And with Kp, you work with partial pressures. So you've got this expression here. That can be broken down into that. And then that can be simplified down into that. So once you've got this set up, again, let's go through the change. So let's say I were to change the pressure in the system. Now the pressure isn't down to one particular reactant or product as such. You just increase the pressure of the system as a whole, or decrease it, and vice versa. So if we were to increase the pressure of the entire system, the only place where there's an expression for pressure is this here, right? So we increase this value. Now, if we increase the value of this P, we increase the value of this whole term here, because they are linked to each other, they're multiplied to each other, so that's linked. So in essence, I am increasing the value of the denominator for this fraction. If I'm increasing the value of the denominator, I am decreasing the value of Kc. Okay, again, I am making a change to the number of particles here. Okay, and therefore, and one of the ways you could increase pressure is by, for example, introducing more particles of a certain substance. So, increase the pressure here, because that's linked to that. The denominator increases and the Kc value goes down. So what does the system try to do? So it's clearly got a high mole fraction of B here, right? Attached to this value of P. Therefore, it causes B to react, or the greater amount of B to react, drives the forward reaction at a faster rate, therefore decreasing the amount of B, or the mole fraction of B, and increasing the mole fraction of the products. So denominator goes down, numerator goes up. Both those things have the effect of increasing the value of the overall fraction. So Kc goes up and restores itself to the original value. Okay, so and then with pressure as well, if you have, let's say, equal number of moles on both sides, you can see there's no pressure term. So therefore, increasing the pressure has no effect on either the numerator or the denominator values on Kc. Okay, right, moving on to temperature. So with temperature, it gets a bit interesting. So here's the initial setup. You've got this reaction here. I haven't got the two multiple here, so it's just A plus B gives you C plus D. It happens to be a gas, but it doesn't really matter when it looks when we're looking at temperature. So you've got an enthalpy value of minus 500 kilojoules per mole. So that means it's an exothermic reaction. So the forward reaction is exothermic. Okay, remember that's always the if that's negative, if the enthalpy value is negative, that means the forward reaction is exothermic. If the enthalpy value is positive, that means the forward reaction is endothermic. So exothermic that way, endothermic that way. So we've established that. So now, if we were to increase the temperature of the system, here's the key thing. We're not actually making a change to the concentrations of any of our substances. Okay? We're not making a change to the concentrations of any of our substances. So, we increase the temperature. The system would like to decrease the temperature. Hence, it increases the rate of the endothermic reaction, because endothermic reactions absorb heat. Okay, they get rid of that heat. So, therefore, how does it do that? It does that by shifting the equilibrium to the left in this case. If the equilibrium is shifted to the left, what happens? We get a decrease in the concentration of the products, if you like, and an increase in the concentration of the reactants. In both cases, right, so if the numerator goes down or the denominator goes up, both those things decrease the value of the overall fraction, okay? So the value of Kc goes down. There's no restoring effect. Okay, so it's a permanent change in one direction. Okay? Likewise, if the opposites happen, okay, let's stick with this reaction. And let's say, for example, we tried to decrease the temperature. And if we try to decrease temperature, the overall the temperature of the system tries to increase the temperature, so increases the rate of the exothermic reaction. So what does that do? It decreases the concentration of A and B and increases the concentration of C and D. Both those things have an effect of increasing the value of the overall fraction, right? So in scenario 2, the value of Kc increases. Okay? Permanently and without reverting back. And finally, you've got catalysts. Well, catalysts don't change the concentration of the reactants or products. All they do is they lower the activation energy such that more particles in the system have the required energy to react, and that doesn't affect the concentrations, and therefore it doesn't affect Kc. Okay, nothing. You could almost argue that nothing more is created or used up or produced or used up because the rate of forward and reverse reactions increase equally.